Hello everyone, welcome to the Foundations of Engineering 1 class. Today we are going to cover chapter 8, Universal Unit. Before we go to chapter 8, let's look at the type of the numerical notation. As I mentioned before in the previous class, there are 4 different types of numerical notations. The first one is standard notations. Standard notation is just standard. As you can see, the number here, 12,345.67. This is just the normal way to number are written. Another way we can use the scientific notation. As you can see, we can convert this standard notation into scientific notations. So here we can see the format of scientific notation is m times 10 to the nth power. Okay, this value of m should be higher than 1 and less than 10. In engineering notation, it's the same format, m times 10 to the nth power. But one different thing between the scientific notation and the engineering notation is the value of m should be higher than 1 and less than 1000, because we have to keep the number in the superscript of part should be multiple of 3. Okay. In calculator notation, we can write this standard notation into the using the E notations. So E is the meaning of times 10, and this 4 is superscript. So times 10 to the 4th power. Okay. So this is what we learned before. And let's review the let's review the lab number 7 that we were done last week. So this is a SI prefix table. In the midterm, I will give you this table so you can see as a reference, like 10 to the 3rd power is a kilo, right? It's a small k, and the 10 to the 6th power is mega, and the large m. In the negative term, 10 to the negative 3, negative third is a milli. The symbol is lowercase m. Okay. So let's look at some examples. We have 2 numbers in standard notation, 0.0698 meters. So how can you convert it into the scientific notation? The value of m should be higher than 1 and less than 10. In engineering notation, this value can be higher than 1 and less than 1000, but as you can see, this superscript number should be multiple of 3. So in this case, in scientific notation, we have to change this value either 0 or negative 3. But if we put the 0, then this value let's see, that if we go to the negative 3rd, then we can create the value like a 69.8. Okay, how about if we put the 0, then it's 0.0698, right? So it's less than 1. Based on the definitions of engineering notation, this value should be higher than equal to 1. So we should keep the number here superscript as negative 3. Okay. If we convert this in engineering notation, we can find we can convert easily into SI prefix. So this value is, this negative third is, if we go back to the previous slide, negative 10 to the negative 3 is milli, right? The small m. So 69.8 millimeters. 69.8 millimeters. It's a short version. Okay. Same here, you can see the m times 10 to the nth gram. This m, the value of m should be higher than equal to 1 and less than 10. But here you can see it's less than 1000, so it's feasible, and the superscript number is multiple of 3. It's 9. It's great. And also we can convert this to using the SI prefix. So it's 501 gigagrams. Shortly we call it GG. But this G is uppercase because, as you can see the previous page, the giga symbol is uppercase G, not lowercase g. So that's why we have to use 501 uppercase G and this lowercase g. This is the femto. Femto is, as you can see, times 10 to the negative 15. But if we want to change it into scientific notation, the value of m should be less than 10, right? So we have to move the decimal place, move forward 2 places, so that the superscript is 6.02 times 10 to the negative 13. The other questions is finding the longest distance. We have 4 examples, and these 4 examples has different units. Someone is miles, the other one is kilometers, yard, feet. So which one is the longest distance? We can always convert this unit to kilometers. In this case, in B, we don't need to convert it, just 40 kilometers. The others, we need to convert it in kilometers. In kilometer, we found that 26.4 miles is the longest distance among the others. Okay, 42.5 kilometers. How about the largest volume? These are the unit of volumes. So gallon is volume, liters volume, cubic meters is volume, cubic feet is also volume. We can convert it into cubic meters. Okay, so 50 gallons is equals to 0.19 cubic meter, 0.10, 1.5, 0.07 meter cubic meter. So in this case, we found that the third one is the largest volume. How about the speed? As you can see, we have 4 different units. One thing is centimeter per second, kilometers per hour, miles per hour. So let's normalize our unit into the meter per second. So 0.5, 0.7. So 0.7 is the fastest one. Last one is the volumetric flow rate. So you can see 10 centimeters per minute. Okay, 1 cubic inches per second. Let me see. Oh, it should be cubic centimeters. It should be cubic centimeters. And the gallons per hour, cubic foot per minute. So we can convert it volume divided by times the volumetric flow rate. So fastest, the largest one is this. Okay, number B. Next question is a pump. Have you ever used a pump before to pull up the water? Let's say if there is a pump and there's a capacity of this pump. It's 70 gallons per minute. This pump can pull up the water 70 gallons per minute. The question is, what is the volumetric flow rate in the unit of cubic inches per second? So we have 70 gallons per minute, and how can you convert it to the cubic inches per second? That's the question. So we have 7 gallons per minute. 70 gallon is equals to the 16,170 cubic inches. And we also want to convert this minute to the second, right? So here it's equals to 1 minute is 60 seconds. So we can just divide it. It's 270 cubic inches per second. Well, actually, I found a pump through Google. It says this pump has a capacity like pumping 70 gallons per minute, and the price is higher than $1,700. Okay. And the next question is fundamental dimensions. As you can see, we have 3 different dimensions. Rho is density, unit is gram divided by centimeter, cubic centimeters. Energy, the unit is joule, and the volume, unit is cubic meters. Okay, we have 3 different dimensions. If we combine them like using these equations, then the question is, what is the final dimensions would be? Okay, for example, the E, you can see is energy is mass times length square divided by times square. Okay, and the volume is cubic meters. So meter is length. So in this case, we can just simply say L cubed. And rho here, gram is mass and the centimeter is length. So we can simply say M divided by length cubed. Okay. So this looks a little bit quite confusing, but once we arrange the positions, numerator, denominator, multiply this, and we can erase the same things, and then we can finally get a square here, and we have a square root here. So last, the answer is L over T, which is the velocity. One gallon of paint. So think about if we have a 1 gallon of paint. How much area that we can cover with 0.1 centimeter thickness? Okay, that's the question. But we have to find the surface area in in square feet. Okay, it's area, so that's why there is a second term is here. As you may know, 1 gallon is 3,785.41 cubic centimeters. These cubic centimeters is actually volume. Volume is, the definition of volume is the area times height. In this case, it's thickness. Okay, so this is the area, and this should be height, because the height is already known. We don't know the area, but we already know about the volume, so this is easily calculate the area in square centimeters. Okay, just square centimeters. So what we need to do is changing this square centimeter into square feet. So 337,000, we can just divide the two terms. We can just using the root equation, and square centimeter. Centimeter square is centimeter times centimeters. Okay, so simply we can convert it. This number we can convert it into the feet. 6.38. 6.38. So the area is 40.7 square feet. That's the answer. Let's look at the question about the gravity. The question is, what is the value of gravity at an altitude of 20 miles away from the Earth? Okay, here we have all the values. So G0 is actually 9.8 meter per second square. The RE is the radius of the Earth, so 6,380 kilometers. 6,080 kilometers. And what we know is altitude, but in miles. So we need to convert these miles into kilometers so that we can calculate easily, find this number, and then we multiply 9.8. The answer is 9.7. So think about if we largely away from the or highly away from the Earth, very close to the space, 20 miles is very long. Okay? Then the gravity is slightly decreased. It keeps decreasing. So the next question is very similar question, but which altitude? What is altitude in this case if the gravity is 9 meter per second squared? Okay, so we can guess the altitude A should be more higher than 20 miles. Okay, we can calculate 172 miles. Let's go to the chapter 8, Universal Units. In this class, we will only cover the half of the chapter 8. There are 6 dimensions: mass, weight, force, density, amount, and temperature. So we will see the definition and what is the characteristics of each individual unit. Okay. Probably you may remember this table that I showed you last time. SI is International Standard. AES stands for here American Engineering System, and the USCS, United States Customary System. So we have 3 different systems, it depending on which country you're living in. But in the International Standard, the standard unit for length is meter. How about AES? In the AES system, foot is the standard unit for length. Foot length. Okay. But here you can see slug. What is the slug? Is it international? Is it some standard unit for mass in USCS system? So I found what is the slug is. I found these images from the Google, and you can see one slug is pretty big. One slug is actually 32.2 pounds, and one slug is equals to 14.6 kilograms. It's very big size. Okay. Anyway, let's look at the mass. Let's look at the differences between mass and weight. So mass is actually dimension of how much, okay? And weight is mass times gravity. So that means mass is not equals to the weight. Mass is mass, weight is weight. Okay. So I will give you one simple example. We have 2 I'm not so sure the word is it. So we have Earth and Moon here. Let's say we have a 10 kilogram dumbbell. But as you can see, the gravity on Earth and the gravity on Moon is quite different. So this 10 kilogram dumbbell can be weight on the Earth is 98 Newton, because 10 times 9.8 meter per second squares. So mass is 10 kilogram. On the Moon, the mass is the same, 10 kilogram, but weight is 16, because the gravity on the Moon is almost 1/6 times smaller than the Earth. Okay. So let's look at the force. So force is mass times accelerations. So it's based on the force is Newton's second law. The unit is Newton. The force is equals to weight. Weight is mass times gravity. So here we have two simple examples. If we push if we push a cart with the same amount of force, and if we push a car with the same amount of force, this cart can get easily accelerated because the mass of this cart is way smaller than car. But car is very heavy. The mass is very big, so that's why I put the big M here. So if we push the same amount of force, then car usually don't move, or very slightly increase the accelerations if you push the car really hard. That's the things. And this is one of the examples that I'm going to showing is NIOSH lifting equations. So my research area is human factors and ergonomics. In our research domain, well, we want our workers at the workplace, they don't hurt when they're lifting some heavy stuff. So for example, if this person lifting a small box, which posture is correct or incorrect, and also this lifting equation is once we know the weight of the box, then we can calculate how much moment or how much torque will be exerted on the joint locations of the human's body. That's the we can solve that problem using equations. So that is NIOSH lifting equations. The purpose of this lifting equation is try to understand how much load can be exerted on a certain joint locations. So try to minimize musculoskeletal disorders. So Newton is a unit of force, and here we have another unit of force, which is pound force. A pound, there are small f subscript. What is the difference between the pound force and newtons? So in the International Standard Unit, SI unit, 1 Newton is 1 kilogram times 1 meter per second square. In AES system, 1 pound force is 32.2 pound mass times feet per square second. Second square. Okay. So a kilogram, 1 pound, 1 meter per second square. This is 32.2 feet per second square. But here, one thing you have to remember is that the pound mass is mass. Okay, you can see the difference here. Pound force is actually force, it's not mass. Okay, so remember these are different, and also the dimension is different. Oh, this is very important. Maybe in the midterm, I will definitely ask this question in the midterm. Ultra straw weight. So let's look at the question. A professional archer is designing a new longbow with a full draw weight of 63 pound force. Okay, this is force, right? It is not mass. 63 pound force. So what is the question? The question is we want to convert this 63 pound force to newtons. Okay, here you can see 1 pound force is 32.2 pounds mass times feet divided by second square. 1 newton is 1 kilogram times m divided by second square. So what we need to do is we need to convert this pound mass and feet to kilogram and meter respectively. So answer is 63 pound force is equals to 63 times 32.2 pound mass times feet over second square. So here we can convert this pound mass into the kilogram. It's 0.4536 kilogram. Okay, and then next we can convert this feet to the meters. So 1 feet is 0.3048 meters. So what we need to do is just multiply these 4 numbers. Then we finally get 280 kilogram times m per second square. So this is actually, you can see, it's 1 newton, right? So this is newton. So the final answer is 280 newtons. Let's look at the density. Let me ask you a question. We have 1 cubic centimeters of gold, and we have also 1 cubic centimeter of aluminum. Which one is heavier? I think some of you already have some answers. Gold is much heavier than the aluminum, even though they have a same size and same shape, same amount. Why? Because of density. Gold is more dense than the aluminum. Here you can see the equation. The density law is equals mass divided by volume. Okay. Let's say water as a let's say water as a reference. Okay. So let's say water is 1 in terms of density wise. If water is 1, then we can find other materials density according to the water. Okay, so mercury is 13.6 times more dense than the water. Gold is 19.6, but air is 0.01. It's way less dense than the water. I think most of you are taking the chemistry class right now, so you probably heard about the amount. The mass is dimensions regarding how much. So let's say mass is the gram is the mass and kilogram is mass, so that is represent how much it is. But amount is a little different. This is how many it is. So unit here amount is moles. 1 mole is equals to 6.022 times 10 to the 23 units. So, scientist, his name is Avogadro. He found this unit. So Avogadro's number is 6.022 times 10 to the 23 units per mole. Alright. So what is 1 mole? So think about it like this. If we have 6.022 times 10 to the 23 tennis balls, then we can say we have 1 mole of tennis ball. Well, if we have 1 mole of tennis ball, we probably can cover all the land area of our Earth. So this is the concept of the moles. Then what is the atomic mass unit, shortly AMU? So AMU is mass of 1 nucleon. What is nucleon? Nucleon is 1/12 of the carbon-12 atoms. I'm not so sure why they take the carbon-12 atoms as a reference, but anyway, the 1 nucleon is mass of the 1 nucleon is AMU. Here, 1 AMU is 1.66 times 10 to the negative 24 gram. It's really harder to memorize, but you don't need to memorize this. You don't need to memorize how many moles has how many units in the 1 mole. So you can just simply multiply these two values. You can see this is 1 mole and this is 1 AMU. So the answer is 1 gram. That means in carbon, 1 carbon contains 1 mole of carbon contains 1 gram. Let's see some examples here. So we have H2O. H2O, as you know, H2O is water, right? So we have 2 hydrogen and 1 oxygen. That is H2O. 1 hydrogen has 1 AMU and 1 oxygen has 16 AMU. Okay, so 1 oxygen is much heavier than the 1 hydrogen. What is the 1 mole of the hydrogen? 1 mole of hydrogen is 1 gram. Okay, and the 1 mole of oxygen is 16 gram. Can you follow this? Okay, so let's look at some examples. Let's assume we have 50 grams of oxygen. So as I said before, 1 mole of oxygen is 16 gram and 1 mole of hydrogen is 1 gram. The question is, how much mass of hydrogen is needed in gram? So if we have 50 grams of oxygen, that means we have 3.125 mole of oxygen. Can you follow this? So we have 50 gram, that means 1 mole of oxygen is 16 gram. So we can just simply divide this 50 gram divided by 16 gram. That is how much more we have of oxygens. So think about the water, H2O. If we have 3.125 mole of oxygen, then how many hydrogen do we need? Yes, we need 6.25 mole of hydrogens. That is 6.25 gram actually hydrogen. So that is the answer. Let's look at the caffeine. Caffeine is more complicated than water, as caffeine contains 8 carbon and hydrogen, nitrogen, and 2 oxygens. Okay. So question is, determine the mass in unit of grams of 0.025 moles of caffeine. So let's look at how many gram in 1 mole of caffeine. 1 mole of caffeine is 12 gram for carbon, and we have 8. It should be 8 carbons, right? And 1 gram of hydrogen, and we should have 10 hydrogen. 14 is 14 gram for 1 more nitrogen. Okay, we should have 4 nitrogen, and 16 is 1 more oxygen, 16 gram, and times we need 2 oxygen to build a caffeine. So calculate this. 1 mole of caffeine is 194 gram. 194 gram. Then what is 0.025 mole caffeine? You can simply multiply 0.025 here. That is 4.85 gram. Okay. The last concept is temperature. These two guys are very famous guys because they invented Celsius and Fahrenheit respectively. Celsius guy, he think about the 0 degree is a freezing point of water and 100 degree as boiling point of water. But in Fahrenheit, he think about the 0 degree is freezing point of mixture, salt and ice, and the 100 degree Fahrenheit is body temperature. Just a little reference, but yeah, they use the reference to determine the 0 degree and the 100 degree. As you probably know, we can convert Celsius to Fahrenheit and Fahrenheit to Celsius using certain equations here. So Fahrenheit is equals to 1.8 times Celsius plus 32. So we can easily convert, and vice versa. So here is all the history. Death Valley in California. In 1913, July 10, the Death Valley is recorded as the hottest place in the United States. It was 56.7 degrees in Celsius. Then what is this Celsius degree in Fahrenheit? We can add this Celsius times 1.8 plus 32, so that is 134 Fahrenheit degree. It's very hot. And let's look at Corpus Christi. The Corpus Christi in 2011, August 28th, the highest temperature was recorded as 107 Fahrenheit. Okay, Corpus Christi, hottest temperature here. Okay, 107. Record high temperature. Okay. So we can convert this Fahrenheit to the Celsius. So Celsius is 41.6 Celsius. So today we learned what is the mass and the weight, what is the difference between mass and weight, and also we learned force, density, amount, and the temperature. Thanks for watching this short video, and have a good day.